Okay guys, so today we are going to go over some graphing skills used in AP Biology. So we started going over some different graphs and analyzing them during class, but I wanted to give you guys a specific assignment just on graphing. So on your canvas, you guys will find this little gem here. We're just going to go through like 2 problems on here, and then I'm going to go and do kind of like my own problem. And I think that'll help you out with both this and then your FRQs later on. So number 1 gives you a graph here. I know it's a little cockeyed, but what parts are missing? Well, there's 3 parts missing from that graph. The first thing, we always need a title. Okay, title. Second thing, we need to label our axis. All right, so we're going to have the x-axis. That's going to be our independent variable. And then our y-axis, that is going to be our dependent variable. And make sure when you label these, if you need to put in units like grams or grams per centimeter cubed for density or liters, something like that, if it requires a unit, put a unit in, okay? If it doesn't require a unit, make sure you have something to distinguish what you're talking about. If you look down here, it goes from 20 all the way to 75. I have no idea what they're talking about. Are they talking about the density of something in grams per centimeter cube? Are they talking about kittens? Nobody knows, okay? So just different things you have to have on a graph. Okay. So here is some data they gave us. You guys have to determine what is the best graph to use given whatever data you have. In this one, we have 3 different parts of our little table here. We have depth in meters, bubbles per minute in plant A, and bubbles per minute in plant B. So if we stop and think what's going on here, I'm guessing it has something to do with maybe photosynthesis rate. There's bubbles coming off of a plant. Obviously those bubbles are probably oxygen. And if we're talking about depth, that means they probably have that plant submerged in water. So it's still photosynthesizing in the water, but yeah, it's kind of nice to count the bubbles because we can actually see the oxygen coming off. All right. Now, what you guys want to determine is, would a line graph be best? Would a scatter plot be best? Would a bar graph be best? Most of the time, guys, it's going to be between a line graph and a bar graph. Okay. So in this one, what's going to be our dependent variable? This is probably going to be our bubbles. And why did we pick this answer? Well, we don't have control over that. We are changing the depth that the plant is in, how far down it is in water, and that is making the change in the amount of bubbles. What's our dependent variable? That's the depth. And this is what we have control over. Okay, we have control over the depth of the plant. What type of graph would be best for this data? Well, if you guys look here, it shows that as we change the depth, our number of bubbles is also changing. I would do a line graph for this. I think that one would be best because we'll be able to see that change, and we only have bubbles that we're dealing with. It's only one thing we're dealing with. So I think a line graph would be best. And then in a graph, you may need a legend. Sometimes you don't need them, especially if you're only dealing with one thing. But usually in an experiment, we're going to be dealing with more than one thing. We only want one variable in that experiment, but we're going to have a control group and an experimental group, and hopefully both of those groups are being graphed so we can see a difference between them. Okay, so that's for number 5. For a legend, we have 2 different plants we're using here. I would probably have 2 different lines or 2 different colors. Okay, you can either do like, if you're using one color, you could do a solid line for plan A and a dotted line for plan B, or just use two different colors. Okay, so here is our graph. I'm not going to keep scrolling up for the video, guys. Okay, you guys can kind of have that on the side. I have mine on a little paper right here, so I will be looking at that in order to come up with my graph. Okay. Now, when you're making a graph, something you want to do is you want to fill up the graph. I cannot stand when I see graphs and it's like, okay, I got all this room here, and my line goes like, okay, there's my graph. No, that doesn't tell us anything. You can't see anything from that. It's much too small to get any good data out of it that can be used as a comparison to the other group, okay? So you want your graph to fill up as much of this space as possible. So let's talk about how you do that first. What I like to do is I like to count my blocks. So if we count the blocks going over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay. On our x-axis, I have 30 blocks. Just make sure we have the same amount going up. 3, 6, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 29, 30. Okay, so I got 33 going upward. Okay? So let's determine what we are going to put on each of our axes. So our independent variable is depth. So we're going to put that on our x-axis. And in parentheses, I'm going to put an m for meters, so we know that that depth is in meters. And on our y-axis, we're going to have bubbles per minute. Okay? Okay, so let's go back to the blocks here. I have 30 going across. What you're going to look at is your highest number for depth. Now, if you look at your highest number for our depth, I have 30. So what you're going to do is you're going to take that number, your highest number, and you are going to divide that by how many blocks you have. Now, obviously, 30 divided by 30 is 1. What that tells us is each one of these blocks can be equal to 1. So I'm going to start at 0. I'm not going to label every one of these. There's no reason to. 1, 2, 3, 4. So I'm going to say this one right here is 5. 2, 3, 4, 5. Okay, 10. 2, 3, 4, 5, 15. 2, 3, 4, 20. 1, 2, 3, 4, 5, 25. And then lastly over here, we have our 30. Okay. And I'm going to do the same thing with our x-axis here. So I'm going to look at both of my bubbles, plan A and plan B, and I'm going to find the highest number. So if you look at yours, the highest number should be 50. Okay. So when you divide 50 divided by 33, you get a number like 1.5. Okay. Now, what you want to do with that number is you want to round it. Now, it's a little different than our normal rounding rules, because even if it was 1.4, we want to round it up to 2. Even if it was 1.4, we're never going to round down with these. Why we're not going to round down is because we will run out of blocks. So I'm going to label these. Again, we're starting at 0. 1, 2, 3, 4, 5. So right here, 5 blocks up, each block is 2, so that block is going to be 10. 1, 2, 3, 4, 5. That block there is going to be 20. 1, 2, 3, 4. That block there is going to be 30. 40. 50. And 60. So I know our highest number is 50. I know that it doesn't go up all the way to the top, but we are using most of our graph. Okay. Now, we got our x-axis labeled, we got our y-axis labeled, we got all our numbers labeled. The one thing we are missing before we start graphing is our title. Okay. So we could do, I don't know, something with photosynthesis. Okay, maybe like photosynthesis rate at different depths. So there's our graph there. And then over here, I will put our legend. All right, I'm going to use two different colors here. We will say the red line is plant A, and we'll go with green for plant B. Okay, so let's get our line going here. At depth 2, so I'm going to start with my red line, plant A. At depth 2, plant A had 29 bubbles. I'm going to come over to the number 2 here. We're going to go up to 29, which is right here. Put a little dot in there. Next one was 5. At 5, it was 36, so 30. Each one was 2. 1, 2, 3. Okay. At 10, it was 45. About right there. At 16, it was 32. And then at 25, it was 20. And lastly, at 30, it was 10. Okay, so let's connect all of our lines here. Boom, boom. And then we're going to start to go down, down, and down. Okay. Plant B. So let's switch our colors here. At plant B, at 2, it was 21. So right there. At 5, it was 27. At 10, it was 40. At 16, it was 50. At 25, we started to decrease. It's at 34. And then at 30, it was 20. Okay. Connect these guys together. Sorry, it's hard to draw lines on this thing. Okay, so there is your graph. Everything is done. We can see the difference between our two plants. Okay. Now, what does this show us? I know there's no, big questions on that on your paper, guys. But what does it show us? Well, if we look here, the plant B actually has a higher photosynthesis rate at a deeper depth. And if you notice with plant A, as we get deeper past 10, it actually starts to decrease. But for plant B, that doesn't happen until after 16, okay? So just difference between our two plants. They're able to photosynthesize at different depths. Could it be oxygen or carbon dioxide levels are different at different depths? Maybe. Maybe some plants they photosynthesize differently. Maybe it has nothing to do with carbon dioxide at all. So just so you guys can see, different plants, different amounts there. Okay. So now let's go to something else. So that's when a line graph is best. There's a good bit on line graphs. I'm going to talk about this guy next, okay? So instead of doing it on here, I'm going to do it on this guy. Okay, so here's what we're going to do here, guys. Let's pretend we are up north a little bit by the Great Lakes. Okay, so let's compare trout. I don't know. We'll do trout size in Lake Michigan compared to Lake Superior. Okay. So let me give you some data here. And again, we're just doing trout size. Let's switch my colors here. We'll start off with Lake Michigan. Okay. So I'm just making numbers up, guys. We'll say in centimeters. I don't know. We'll say the average trout is 25 centimeters plus or minus, let's say 5.7 centimeters, okay? And then let's say for Lake Superior, maybe the average is 21.2 centimeters with a standard deviation of 2.6 centimeters, standard error. Okay, so what they're going to give you is this first number here. This is going to be our mean. So we took all of our numbers, added them up, and divided by however many trout we looked at, okay? That's an average. This over here is going to be our standard error. And the standard error is going to be your standard deviation divided by the square root of our numbers, a number of trout we have, okay? So it's real close to standard deviation. So let's make our chart here. Okay. So for this one, guys, we're comparing two things. And we don't have a whole slew of numbers that are increasing and decreasing. So in this example, our best thing to use, our best type of graph, would be to use a bar graph. Now, bar graphs are going to be a little different in AP than they were in your previous classes. So for our dependent variable, on our y-axis, we're going to have trout size in centimeters. And then down here, do them in different colors again, we will have, I'm going to do LM for Lake Michigan. And then we'll do LS over here for Lake Superior. I do not need to do any numbers down at the bottom. We're good, okay? Title, we'll say comparison of trout sizes in 2 Great Lakes. Okay. So next thing I'm going to do, let's make our lovely numbers on the side here. Now, what you want to do, as I said, you got to look for the highest number in the line graphs. Bar graphs are a little different. This plus or minus, you want to see what your highest number is going to be when you plus or minus these. So yeah, 25 is our highest number, but our highest number is actually going to be 30.7. So if you do 25 plus 5.7, we get up to 30.7, okay? So just a little rough thing I'm going to do here. We'll say this is 5, 10, I'm not going to write them all out, 15, 20, 25, 30. Let me fix this because this is going to annoy me. Okay. We'll just do 10. And this will be 35. Oops. And all the way up here will be 40. Cool. Sorry guys, I'm screwing up on this one. There we go. Okay. So let's start off with our Lake Michigan fish. So we're going to have a bar graph, and we are going to make the bar graph as normal based on our mean. So nothing crazy yet. So we're going to go down. I'm sorry, my lines will not be straight. Okay, now there you go. That is going to represent our mean, our average. Now, the next thing is we are going to put our lines in. It's like almost like a box and whisker plot here. What we want to do is we want to put a line at 30.7, and then we want to put a smaller line at whatever 25 minus 5.7 is, okay, which is, what, 19.3? So at 19.3, which is about right here, we're going to put a little dash line, and then at 30.7, probably about right here, we're going to put another dash line, and then we are going to connect them, just like that. I will explain to you what these mean in a few minutes. Let's do the other one first. So 21.2, maybe like right here for Lake Superior. Okay. If we do 21 minus 2, or 21.2 plus 2.6, we get 23.8, which is probably about right here. If we do it the other way, where we subtract, about 18.6 there. So that number is going to be about right there. Okay. Connect your lines. So these are our mean graphs with our standard error on both sides. Okay, we have an upper standard error and a lower standard error. So what does this all mean? Well, if we analyze this data, guys, you guys can see that obviously the mean of fish is much bigger in Lake Michigan compared to Lake Superior, because right here is higher than right here, okay? But what do these these standard error lines mean? Well, the bigger they are, or the further apart they are, okay, you can see how big this one is compared to this one. All right. This means that their sample size of fish were not really isolated around that number of 25. We had some that were a lot smaller than 25. We also had some that were a lot bigger than 25 in Lake Michigan. But if you look at Lake Superior, right here, if you notice, that's a very small standard air. That's fine. Standard air line. What that means, guys, is that our fish, all of our fish in Lake Superior, are pretty darn close to around that 21.2 centimeter number. Okay, so that's how you do a bar graph in AP Bio. All right, a little different than our bar graphs in the past, but these are your two ones you guys have to know how to use. Bar graphs, line graphs. We'll go over some other ones later on in the year with whisker box plots and all that kind of stuff. Anyway, make sure, guys, anytime you're making a graph, label your axes, your X, your Y, put a title on, try to expand your graph as big as you possibly can to fit the area. Don't make small graphs. All right, hopefully this helped you guys for your graphs. Have a good rest of your day.